Divergence theorem. Divergence theorem says that the double integral of f dot n ds over some region S is equal to the triple integral over some region Q of the div of f dv. Under the following conditions, it has to be that Q be a solid region bounded by a closed surface S, orientated by a unit normal vector directed outward from Q. It has to be outward. If F is a vector field whose component functions have continuous partial derivatives in Q, then this is true. Okay. The object is to work out problems. Suppose you're asked to verify the divergence theorem. That is, do the given integral this way, compute it that way, and say, hey, they're actually equal. Suppose that you're told that f of x, y, z is equal to 2x minus 2y z squared. 2x minus 2y and z squared. And S is a cube bounded by the planes x equals 0, x is a, y is 0, y equals b, and z is equal to 0 and z is equal to a. Y should just go out to a. It's a cube. Everything x, it's all the xy points where x is between 0 and a, y is between, maybe I said that wrong. It's all the xyz points where x is between 0 and a, y is between 0 and a, and z is between 0 and a. Okay. Now, what we need to understand is, let's just have some language down. First, the cube, of course, has 6 sides. You have the front, the back, the top, and the bottom. When it comes to the top, z is 0. No, z is a. Z is a. I guess the origin is right here, 0, 0, 0. At the top, z is a. I know at the bottom, z is 0. So at the top, z is a. And n is going to be going straight up, so n is just positive k. So then f dot n. F is right here. And n is 0, 0, 1. That's n. And when you dot them, you get z squared. 1 times z squared. Then, but remember, z is a. So it's the integral of f dot n, which is a squared dx dy. And x goes from 0 to a, and y goes from 0 to a. If you work this out, you get a to the 4th, 0 to a. Okay, that's the top. What about the bottom? The bottom is where z is 0. And normal would be negative k, because the normal is coming straight down. It's in the k direction, but it's negative. Well then, f dot n. N is 0, 0, negative 1. And when you got it with f, negative 2x times 0 is 0, plus negative 2y times 0 is 0, plus z squared times negative 1, that's negative z squared. But z is 0, so you get 0. And if you integrate, you're going to get 0. If f dot n is what you're integrating is 0, if this is 0, the integral is 0. So that's the bottom. So we did the top, we did the bottom. Now let's do the front. Since the bottom didn't contribute anything here, let's do the bookkeeping on top. So far, we got a to the 4th. Plus 0 is still a to the 4th. Now let us do the front. We'll call front and back the x-axis. So when it comes to the front, that's when x is equal to a. And n is going to be positive I, because it's coming out. It's going in the positive x direction. So n is 1, 0, 0. So that's the 1, 0, 0. So f dot n, this times 1 and these times 0, add them up, you just get 2x. But x is a. So it's the integral, the double integral of 2a dx dy. X goes from 0 to a, 0 to a. You're going to get 2a cubed plus 2a cubed. So plus 2a cubed. That's the front. The back, you're going to have x equals 0 in the back. And n would be negative I. That is, it'll be negative 1, 0, 0. So f dot n is just negative 1 times 2x. It's negative 2x. But x is 0. So f dot n is 0. That's going to integrate to 0. The integral of f dot n ds, well, it's a double integral of 0 ds. It's 0. So the back didn't contribute anything. Now we go left and right. Okay, so now we have to do left and right. Since y is positive to the left, and y goes from 0 to a, the left will be where x is 0, where y is 0. The left side. That's where y is 0. So y is 0. Remember, y goes in that direction. So y, that's negative j. N is negative j. Okay. So f dot n, that is its I, J, K. So f dot n is negative 2y times negative 1, which is 2y, where y is 0. So again, we're going to integrate 0, and we get 0. Okay, let us now do the right-hand side. That's where y is a, going this way. So the normal is just j. The normal is 0, 1, 0. Dot f with n, only the second components match. That product is negative 2y, but y is a, so it's negative 2a. So we need to integrate negative 2a dx dy. X goes from 0 to a, y goes from 0 to a. But this is the same integral we did before that gave us 2a cubed, except it didn't have the minus. Well, now it does. So we take away 2a cubed. And the answer to the left side, that is computing f dot n ds, the answer is a to the 4th. Everything else was either 0 or canceled out. So that was long and brutal, and we all hated it. Well, the divergence theorem gives us a much, much easier way of doing this. It just says to integrate the div of f. Well, first we have to find the div of f. Now, f was equal to, and so long we don't know, 2x minus 2y and z squared. So the div of f is the partial of this with respect to x plus the partial of this with respect to y plus the partial of this with respect to z. So we just get 2z. We get 2z. Okay, so we integrate 2z. Dx, actually it's a triple integral, dx, dy, dz. X goes from 0 to a, so does y, so does z. 0 to a. This, being not a function of x or y, can come in front two integrals. Dz, 2z. Double integral dx, dy, dz. This innermost integral is just x from 0 to a, which is just a. The a can come in front. How about 2az? 2az. This integral is y from 0 to a, dz. But this in here is just a, times by this constant, 2a squared z, dz. Now this is just a constant. the integral of z dz is z squared over 2. The 2's cancel. Z goes from 0 to a. So we have a squared, z squared from 0 to a. You plug a in, you get a squared times a squared, a to the 4th. You plug 0 in, you get 0. So the answer is a to the 4th. Exactly what we got after doing 10 minutes of work. The divergence theorem, it makes the problem easier to do. You can probably always get away without ever using it, but you might get into some hard integration. So that was a long problem because there were 6 faces of the cube. But it's a lot easier the way we did it, using the divergence theorem. Not much to do in this section. Suppose that you have that f is x, y, z. And you're asked to prove or to show that the double integral of f dot n ds is 3 times v, where v is the volume of the surface. Well, what you should do is find the div of f. The partial of this with respect to x is 1, plus the partial of this with respect to y is 1, plus this partial with respect to z is 1. So the div is 3. So the double integral of f dot n ds is equal to the triple integral of the div, which happens to the div of f, which happens to be 3 dv. This 3 can come in front. Well, whenever you have a triple integral of 1 dv, well, what you get back is the volume. You get back v. This here is v. 3 times v. Exactly what we said we would get. What if you just have a constant? What if you just have a constant? Suppose that f is just a, b, c. Well, then the div is going to be 0. The div of f. The partial of this with respect to x, with respect to y, plus with respect to z is 0. A, b, and c are just constants, 7, 9, and 11. Their partials are all 0. So, the double integral. So the problem was to show that this is 0. Well, this is equal to the triple integral of the div of f dv, which is the triple integral of 0 dv, which is 0. This is 0. Okay, that completes that section. Okay, here's another nice problem you should do. Here's another good problem. Suppose that f is equal to 2x, negative 2y, and z squared. And the surface is the cylinder. X squared plus y squared equals 1, and z goes between 0 and h. So if this is the z-axis, we have the z-axis, we have a cylinder on it. Y, x, of a cylinder. And the height of the cylinder goes up to h. And the radius is 1. From that imaginary line, that center, to a point on the cylinder is 1. Not just any point, it has to be at a right angle. Right angle, this length is 1. So we want to calculate f dot n ds. So when it comes to the top, the top we have z is always h. And n would just be positive k. That is, n is I, j, k. So f dot n, this times 0 plus this times 0 plus 1 times z squared is z squared. So z is h, so z squared is h squared. So it's a double integral over s of h squared ds. But h squared is just a constant, which I want to bring in front. Which I want to bring in front. See if I can live up to that. Now here, this is just the area. It's the area of a circle, a radius 1. This is pi times 1 squared, which is pi. So it's h squared times pi, or pi h squared. So pi h squared. Let's do the bottom while we're at it. The bottom, z is 0. And n is coming straight down. So n is negative k. N is negative k. So now f dot n will be, well, n is 0, I, j, negative 1. It's just negative z squared. But z squared, z is 0. So it's negative 0 squared, which is 0. That means that the integral is 0. So you add 0. Now you have the sides. So far the answer is pi h squared. Now you have the sides. Well, on the sides, you know that x squared plus y squared is 1. So the normal would be partial of x, partial of y, divided by the length, which is the square root of 4x squared plus 4y squared. So let's look at this a bit more closely. You can factor out a 4. And in this problem, x squared plus y squared is 1. So you have the square root of 4 times 1, which is the square root of 4, which is 2. This bottom is just 2. The top, you can factor out a 2. You can factor out a 2. And this 2 will kill off that 2, and you just get xy. So f dot n I guess, you know, it it's 3 dimensions, so you get x, y, 0, sorry. So you get x, y, 0. And that's n. This is n. And when you dot it with f, which is 2x minus 2y z squared, you get 2x squared minus 2y squared. Now, we know S and A. We know that S, the surface area, the circumference, is 2 pi times r, but in this case r is 1. So it's 2 pi. And A is pi r squared. Pi r is 1. Pi times 1 squared, which is pi. So this is another way, pi is another way of writing A, 2A. So S is 2A. If S is 2A, that implies that ds is 2dA. So f dot n ds, this double integral, is going to be the double integral of f dot n is this, which I'll factor out the 2, times ds, which is 2dA. 2dA. And 2 times 2 can be brought out in the front. So we have 4 times the double integral of x squared minus y squared dA. But dA is dx dy. And I guess rather than even saying what these limits are, why don't we just go right to polar? X squared is r squared cosine squared theta minus y is r sine theta, so I have to square it. And dx dy becomes r dr d theta. So I can factor out an r squared and an r, and pull an r cubed out. And since it is circles of radius 1, r is going from 0 to 1, and the angle is going between 0 and 2 pi. And that's the integral that you need to solve. And this was brutal. I don't disagree with that. And I'll tell you in a moment what that integral equals. Because the easier way of doing this is to find the div of f. The partial of this with respect to x, plus the partial of this with respect to y, plus the partial of this with respect to z. And like we got before, it's 2z. So that integral, f dot n ds, is equal to the integral of the div. Actually, we can make it a triple integral. The div of dv, dy, dx. Z they told us. It goes between 0 and h. X, well, the whole circle. It goes from negative the square root of 1 minus y squared to positive the square root of 1 minus y squared. And that should be y's, so this should be x, sorry. And x goes between negative 1 and positive 1. And if you were, I thought this integral would be a snap to do, but it isn't. If you were to do this integral, then you would find out, then this integral is a lot easier to do than the integral that we had at the beginning. F dot nds. This was pretty hard. We actually set it up, we got it down here. And we set up a much friendlier looking integral, I think, over here. And if we converted that to polar or cylindrical coordinates, it'd be a lot easier. That finishes this section. One more to go.